Hey students, this is our first video introducing inclined planes. We're really just going to look at the definition of what an inclined plane is and how and why we're actually going to tweak our approach to setting up our sum of the forces compared to what we've done before. In the next video, I'll actually have a strategy as well as an example problem that I will work out. So first, an inclined plane is really just a fancy word for like a hill. It could be a driveway that's sloped, it could be a roadway, some kind of ramp. It's something that is not perfectly horizontal, but instead raised up some angle, some degree theta. And we'll always refer to it based on this angle above the horizontal. So here I simply have an object that is sitting on an incline. And in this example, just the very most basic one, this orange box, will say it's at rest. It is not moving. Okay? Well, let's first draw a free body diagram of that orange box. Free body diagram. Here's my dot. If you want, you can hit pause and try it yourself. I know, for example, there's weight acting on this box. Sorry for my poor drawing skills. There's also a support force or a normal force. You have to remember that Fn is always perpendicular to the surface. That's why it's called a normal force, because normal in math means 90 degrees. That's supposed to be a perpendicular sign. So normally when we had a flat surface, the normal force would go straight up, Fn. But here, the normal force is perpendicular to this ramp. So if this is the ramp, 90 degrees would look like that. So on my diagram, the normal force, this is the first new thing, is at an angle. That's Fn. Just think 90 degrees to the incline. There's also a frictional force. You probably could have guessed that since the box is at rest. I don't see any strings attached to it, no anchors or anything. So there's a frictional force. Friction is always parallel to the surface of the object. Always parallel to surface. I would write any and all these things down, especially if you didn't know them before. So again, this is parallel. I might have this be my frictional force. And yeah, that's a static friction if the box isn't moving, but I want something going up and to the left. Here is my static frictional force. There are no other forces acting on this object if we ignore like air resistance. There's weight, which is always down. Even put that down. Fw is always, oops, that's an S, down. And then we have the normal force and a frictional force. Okay? Well, usually our next steps would be to break this down into components. And if we're looking at our free body diagram, it looks like we have, frankly, a fair amount of work on our hands, because normally we would be breaking things into the x direction and the y direction. But here on this free body diagram, there's only one force that's actually acting in that normal direction. That's the weight. The weight is acting up and down, or down, okay, as normal. But the normal force is now acting up and to the right, and the frictional force is acting up and to the left. What we would traditionally do is, draw Fn again and break it into its x and y. And then we would repeat. We would draw Fs and break it into its x and y. And that seems like a lot of work, considering the fact that we would be breaking down 2 out of the 3 forces. And so besides drawing the free body diagram and highlighting these facts, I want to look at the next way we're going to approach inclined plane problems. If 2 out of the 3 forces are acting in a direction other than x and y, why would we break it down into our traditional horizontal x and our traditional vertical y? We won't. Instead, since the normal force is acting in this direction and the frictional force is acting along the ramp, up and down the ramp, the general approach is having a new coordinate system, what I'm going to call x prime and y prime. Because if we use these coordinates, Fs, this frictional force, it's acting in the negative x prime direction, and the normal force would be acting in the positive y prime. We wouldn't have to break those down. Now, we would still have to break down weight, because look, now weight is at some weird angle compared to x and y. But now we only have to break down one out of our three forces. Not only that, in this case, the box isn't moving. Okay? But in future problems, we're going to see examples where the object is actually accelerating. Okay, it's speeding up down the ramp, or even if it's moving at a constant velocity. When this box is moving, it's not going to be moving to the right. It's going to be moving down and to the right. So this is also a reason to use this new coordinate system, because this coordinate system is actually aligned with the direction the object is moving, down and to the right. So this is going to be part of our new strategy. Okay? Last time we labeled the coordinates x and y. Now we're going to use new coordinates that are tilted down the ramp, x prime, and then perpendicular to that, y prime. And the nice thing is these are still at 90 degrees. We can still use our SOHCAHTOA trigonometry. So in our next video, one of the things we'll do is we'll actually break these down into components. This is the end for this video for the most part. You can hit stop now and go on to the next video. I have an optional segment which is actually breaking down this FW and showing how this angle theta is related to this downward force of weight. For the last part, I have our box drawn again. And if we remember our free body diagram, it looks like this. I have the normal force, I have FW, and I have this static friction. If we break or I should say, if we're going to use our coordinates down the ramp, as I mentioned, and perpendicular, as I mentioned, we have to break down FW. Here's FW. Now, FW is made up of two pieces. The piece that's acting perpendicular to the ramp, which I kind of have, or I don't actually have it right there. The part that's acting perpendicular to the ramp is this part. Okay, I guess kind of like this. I guess I do kind of have it. Okay, this would be FW broken up in the Y component. The piece that's acting down the ramp, parallel down the ramp, that's FWX. Let me erase this. So here's the original force vector, FW. It always points straight down. This piece right here is F acting in my new X direction, down the ramp, and then perpendicular to the ramp. This ends up being the same angle theta as the angle of my incline. Okay, there's two things you can do. One, if you draw this and you break it into components, okay, so here's my FW. If you always then draw the Y component, okay, if you draw the Y component first, that angle you just made will always be the same angle of the ramp. If you want, you could just remember that. When you break the weight down, the Y component is the one you draw next, and that angle is going to be the same as theta. But what we did over the summer assignment, was actually proving this very thing. This angle theta is this angle right here. And you could pretty quickly prove that this angle has to be the same as this angle. Okay, and that's what I'm going to do right now. If this is theta, the weight, which I have in black, this is kind of the direction of the weight. I just moved it down so we could see it in the context of our triangle. This is a 90-degree angle. So this right here must be 90 degrees minus theta. See that? Because the sum of the triangles has to equal 180. Here is 90. So these two things have to add up to be 90. And if this is theta, this must be 90 degrees minus theta. Well, look at my normal force. This is making a 90-degree angle, which means this whole angle here is 90 degrees. So this piece must be 90 degrees minus 90 minus theta. That's 90 minus 90 plus, if you factor, theta. That's theta. So this angle here is theta. That's why I drew it in there. Okay, you can either do that setup and prove it to yourself every time, or again, I recommend when you draw that FW, draw the y component first. FWY, the piece that's acting now in the same direction, in the vertical direction. And that means this angle here will always be theta. If you draw FW, and then you draw the x component, you could technically, but that would actually then make this theta right here. So that's usually a little trickier. Anyway, we'll look at an example problem in the next video. Thank you.